So, what exactly happens when modern artificial intelligence takes on a mathematical ceiling that's been stubbornly stuck for 70 years? Well, welcome to today's Explainer, where we're going to unpack a truly fascinating breakthrough in pure mathematics. This isn't just a story about an AI crunching a massive set of numbers, it's about an AI actually helping to discover a brand new theorem. We're going to dig into a recent paper that formally lowers a boundary that has literally haunted functional analysis since 1953.
Right, but before we get into the nuts and bolts of how the AI actually cracked this thing, we kind of need to set the stage. What exactly is the Grothendieck constant? Why do mathematicians obsess over this one specific number? And honestly, why has it been so incredibly difficult to pin down for decades?
Okay, let's dive into this. The Grothendieck constant, which you'll usually see written as K sub g, is basically this incredibly stubborn mathematical ceiling. Imagine you're trying to map this complex, perfectly smooth sphere of endless possibilities into a set of rigid, blocky, black and white rules. The Grothendieck constant represents the mathematical cost, or the gap, of forcing that smooth, continuous reality into a strict, discrete format. In functional analysis, it's the absolute limit between a continuous optimization problem and its discrete counterpart. It's a foundational boundary, It shows up everywhere from graph theory to quantum mechanics. And the crazy part? For 70 years, no one has actually known its exact value. To really grasp the scale of this mystery, let's walk through the timeline. Back in 1953, Alexander Grothendieck himself proved the constant had to be less than or equal to roughly 2.30. Then there's a massive leap in 1977. A mathematician named Krivine dropped the ceiling drastically to about 1.78, and he was so confident he actually bet that this was the absolute limit. It wasn't until 2011, we're talking over 30 years later, that a team proved the constant was slightly less than Krivine's bound, but they couldn't even give us an explicit number. Mathematical progress can be agonizingly slow. But that brings us to today, an historic new AI-guided breakthrough that finally explicitly drops that ceiling. Section 2, Strategies for Lowering the Ceiling, How Mathematicians Partition Space. So to understand how the AI pulled this off, we have to look at the actual tools researchers use to push this ceiling down. The secret weapon here is something called a rounding scheme. To solve this underlying matrix inequality, mathematicians use these rounding schemes to map really complex, continuous vectors into simple, distinct positive or negative signs, literally just plus ones and minus ones. You can kind of think of it like slicing up a pizza or drawing borders on a map. You're drawing dividing lines through a complex, multidimensional space just to categorize vectors into simple yes or no camps. Let's compare the classic approach with the modern one here. On the left, we've got the classical Krivine approach from 1977. This uses a hyperplane scheme. It's essentially a single, perfectly flat dividing cut to partition the space. It is super elegant, incredibly powerful, and that's exactly why it stood practically untouched for decades. But look over on the right. Here we have mixed Krivine schemes. Instead of just one flat cut, this approach uses a randomized mixture of multiple partition strategies. Think of it like having a diverse team of detectives. A single flat cut is going to have blind spots, right? But if you assign probabilities to a mixture of different, more complex cuts, they cover for each other's weaknesses. And the underlying math proves that a mixed scheme can actually give you a strictly better bound than any individual scheme could on its own.
Section 3. Enter AI-guided search, automating mathematical discovery.
Let's move to the mechanics and see how this actually builds into an automated discovery engine. Now, you might be wondering, if mixed schemes are the obvious answer, why did it take so long to find the right one? Well, because the search space is impossibly vast. It's like finding a needle in a multi-dimensional haystack. So the researchers deployed an AI coding agent to propose a strategy that decoupled the search into two really efficient stages. Step 1. The AI uses an atom optimizer to draw complex, wavy boundaries through the space. It explores all sorts of different polynomial functions, just to generate these candidate cuts. Then, step 2. Once it builds up a dictionary of good candidates, the AI freezes them. It then uses a second algorithm, sequential least squares programming, to figure out the exact percentage or the weight to assign to each boundary. It dynamically calculates exactly how to blend that classic flat hyperplane with the crazy new wavy cuts. Section 4. The tiger partition illusion, when beautiful math leads to a dead end. Now, what's really interesting here is that before the AI found the actual answer, it fell into this beautiful mathematical trap. Take a really close look at the mesmerizing pattern emerging here.
Researchers were using a mathematical proxy called Koenig's bilinear form to hunt for better bounds. If you follow the sequence from left to right, starting at f0 all the way to f infinity, you are literally watching a mathematical operator being repeatedly applied to refine a completely random partition. And notice how, over multiple iterations, the chaos perfectly organizes itself into these two cycle partitions. They alternate these striking black and orange shapes that end up looking exactly like tiger stripes. It's visually stunning. And because these tiger stripes perfectly maximize Koenig's bilinear form, human intuition strongly suggested that these had to be the holy grail for lowering the Grothendieck constant. But here is the tiger twist. When the researchers rigorously tested these visually perfect tiger partitions to see how they'd actually perform as rounding schemes for the Grothendieck constant, they completely failed. Yeah, they do maximize Koenig's value, but they produce an upper bound on K sub g of about 1.97. That is significantly worse than Krivine's baseline of 1.78 from 1977. It's just a great, somewhat humbling reminder that optimizing for the wrong metric, even if the result is absolutely beautiful to look at, doesn't actually solve the real-world problem you set out to tackle. And this graph brilliantly illustrates that exact decoupling we just talked about. Let's break this down completely, because there's a lot going on here. On the vertical y-axis, we have the Koenig value. Again, that's the old mathematical proxy they were using. And on the horizontal x-axis, we are looking at the ambient dimension. And notice how it scales all the way up to a mind-bending 100,000 dimensions. Now, see that flat red dashed line down near the bottom? That represents the absolute upper limit of the classical 1977 hyperplane method. But then, look at that solid blue curve. That represents the entirely new family of partitions the AI found. Notice how rapidly that blue line rockets right past the red dash baseline, pushing way up past 0.599. This mathematically proves, without a doubt, that you can find partitions that completely shatter the old baseline for Koenig's value. But, as we just learned from those beautiful tiger stripes, winning at this specific metric doesn't guarantee you win the Grothendieck prize. The AI had to look elsewhere.
Section 5. A historic new bound. The final AI deduction. So, completely bypassing those beautiful tiger illusions, the AI got to work on a mixture of the classical hyperplane and complex polynomials. And the math required to lower this ceiling gets incredibly tight. The AI revealed exactly how tight. The researchers tracked how much improvement they got by pushing the polynomials to higher and higher degrees. Notice how the improvement numbers step up on this list, but the size of those leaps gets smaller and smaller every time. Going from a degree 3 to a degree 5 polynomial essentially doubles the improvement. That's a great jump. But by the time we hit degree 7 and then degree 9, the AI is basically squeezing water from a stone. It hit a very clear point of diminishing returns. But it successfully extracted every last mathematical drop of optimization to find a highly complex degree 9 Hermite threshold rounding scheme. So the absolutely crucial point of all this work comes down to this exact number, 6.039 times 10 to the negative 5. That's 0.0006039. Now I know, it looks completely minuscule, but in theoretical mathematics, explicitly carving away even a microscopic fraction from a universal law that has stood completely untouched since the era of disco, that is a monumental feat. This right here is the exact fraction by which that 70-year-old Krivine ceiling was finally explicitly lowered. Which brings us to the new, historic, mathematically certified theorem. The Grothendieck constant is strictly less than this exact formula right here, minus our AI's hard-won tiny fraction. And thanks to something called rigorous outward-rounded interval arithmetic, which is basically a software tool that absolutely guarantees the exact mathematical value is captured, including all possible rounding errors, this new boundary isn't just a really good estimate, it is a mathematically certified reality. So, what does this all mean for us? It leaves us with a truly exciting prospect. This AI didn't just brute force a massive calculation. It successfully navigated a complex landscape full of false proxies and mathematical illusions to literally design a novel algorithm for partitioning space. We are entering an era where AI isn't just a calculator for human ideas anymore, it's becoming an active collaborator, actually discovering the fundamental theorems of our universe. If a 70-year-old ceiling like this one can fall, what's next?